Welcome back to the course Basics of Mechanical Engineering 3. I am here in the first tutorial session of fluid mechanics. This tutorial session is majorly focused upon introduction to fluid mechanics, where I will talk about the pressure differences in manometer. I'll talk about surface tension and some properties of fluids. For example, surface tension is one of the properties, density, capillarity, those parts I will discuss in this tutorial. I am Dr. Amandeep Singh Oberoi from Indian Institute of Technology, Kanpur. Manometer, to recall the concept, I have just jotted down some text here. A YouTube mercury manometer is a classical and widely used device for measuring the pressure of fluids, relying on the principle of hydrostatic equilibrium. It consists of a transparent U-shaped tube that is partially filled with mercury, a dense and a stable liquid, that is property of mercury. One end of the tube is connected to the fluid system whose pressure is to be measured, while other end is open to the atmosphere or another reference pressure. So, there is a reference pressure. Based upon the reference pressure, we have one end of the tube where the pressure is to be measured. The pressure difference between the fluid and the reference causes mercury to move, creating a difference in mercury column heights on the two arms of the U-tube. This part is already covered. Here, for example, the pressure is to be measured of the fluid. This atmospheric pressure that is open on the scale. This difference is known as pressure head difference. This let us know what is the pressure of the fluid system here. To calculate the pressure in the simple U-tube mercury manometer, we use this relation H plus H1S1 is equal to H2S2. So, H is pressure in terms of height of water column, H1 is height of water column on the left limb, H2 is height difference of mercury column on the right limb, that is higher. You could see it is mentioned here. This is H. S1 and S2 are the specific gravity of water and mercury. For water, the specific gravity value is S1, that is 1. For mercury, this value is 13.6. Now, I will draw a simple illustration to show you how all these parameters that we have mentioned here are there in an apparatus setup and how do we measure the pressure difference. The problem statement says a simple U-tube mercury manometer is used to measure the pressure of water in a pipeline. The mercury level in the open tube is 70 millimeter higher than that on the left tube. The height of water in the left tube is this. Calculate the pressure in the pipe in meters of water and in kilonewtons per meter square, that is the exact unit of pressure. So, as it is mentioned here, all these units H, H1, H2 are in length, that is meter. Now, this is a setup where they are telling about. For instance, this is a kind of a manometer, something like this, and from here this is a pipe of uniform diameter, that is here. So, there is a difference here. For instance, I have filled solution from this length to this length. This is filled. Then this difference between this center to this level, this is H1, and this difference from this level on the left tube to the level of the right tube, this is H2. I will just name them as A and B. This is A, this is P point, and there is height H, that is in meters of water. Now, what we are given is H1, which is in millimeters, that is 50 millimeter. So, height of water in left tube is 50 millimeter, H1 is 50 millimeters. To convert them into meters, this is equal to 50 by 1000, that is 0.05 meter. This H1 is 0.05 meter and H2 is also given 0.07 meter. That is given. Mercury level in the open tube is 70 millimeter higher than in the left tube. It is 70 millimeter higher, this difference. H2 is 70 millimeters, that is 0.07 meter. Now, we need to find the pressure in the pipe in meters of water and in kilonewtons per meter square. To find the pressure, that is H, pressure of water, H is to be determined. As we know, H plus H1 S1 is equal to H2 S2, right. I can put here as H is equal to H2 S2 minus H1 S1, right. Now, this could be directly calculated. I am talking about the part A here, part A, which means H is equal to, let me put the values, H2 value is 0.07, S2 is specific gravity of mercury, which is 13.6, this minus H1 into S1, that is 0.05 into specific gravity of water. This gives me the value of H as 0.902 meters of water. Second part is we need to calculate this pressure in kilonewtons per meter square. So, we know pressure is also W into H, that is here W is specific weight of water. Right, there we will put value as 9.81 into 0.902, this turns out to be 8.848 kilonewtons per meter square. So, this is the calculated value here. So, we have H as 0.902 meters of water, that is written already, and in kilonewton per meter square we have gotten the pressure value P as 8.848 kilonewtons per meter square. Now, this was a simple manometer. There is a U-tube manometer as well. For U-tube manometer, let me recall the theory part here. U-tube manometer is a differential manometer. So, U-tube differential manometer is a device used to measure the pressure difference between 2 points in a fluid system. It consists of a U-tube partially filled with a manometric liquid like mercury, both the ends connected to the points of interest, allowing direct visual comparison of the fluid columns. So, here what happens, you can see this diagram here. Now, here both the ends are connected to the points of interest, that is the things which are to be measured. For instance, we need to measure for both A and B the pressure difference. So, here the differential U-tube manometer is there. Difference between A and B, it will tell HA minus HB, that is pressure head at point A in meters of water and pressure head at point B in meters of water. HA minus HB is equal to H3 S3 minus H1 S1 minus H2 S2. So, where is H3 here? That is the distance between the lower and the upper level of mercury in this tube, that is H3, and H1 is for the point A, H2 is for point B, and these differences are from the upper and the lower heights respectively. So, H1 is height of liquid 1 column in meter, H2 is height of mercury column, H3 is height of liquid 3 column. So here S1 and S3 are specific gravity in the fluid that is there in pipe A and B, and S2 is specific gravity of mercury. Now let me say problem statement. It says an U-tube differential manometer is used to find out pressure difference between two pipelines A and B. The pipe A carries carbon tetrachloride of specific gravity this. Pipe B contains oil of specific gravity this. The pipe A lies 2.5 meter above pipe B. The center of pipe B is at the level of mercury in the other limb. The difference in the levels of mercury is 342 millimeter. Calculate the pressure difference between A and B. This is a setup that was just shown in the previous figure, like this figure. So there are two different liquids here, A and B, and there is a connection between them using a U-tube differential manometer. Like this, and it has given the values here. I will just name it as A, name this as B, and this is the center point here. This is the center line here for A and B. The heights which are given here, we have value of H1, H2. H1 is what? 2.5 meter above pipe B. H1 is 2.5 meter, and H2 here is 342 millimeter, which is equal to 0.342 meters. And they say the center of the pipe B is at the level of mercury in the other limb. That means H2 is equal to H3, which is same as 0.342 meters, and we have been given the values of S1, S2 and S3. S1 they say is carbon tetrachloride, which is 1.594. S2 is always mercury, that is 13.6. S3 is given here an oil of specific gravity 0.8. Now, because they say the center of pipe B is at the level of mercury, so mercury is filled till this point here, till the center of pipe B. That is, this is the same level here. So, here the fluid is filled until what level? Till the level H3 here. That means this dimension or height here from this level, this is H2 for mercury, and it is same as H3, right. This is very important line written here. The center of the pipe B is at the level of mercury in the other limb. So that is why H2 and H3 are equal, and from H2 this level we have H1 that I can write here. H1 is here from the mercury to the pipe A. This is H1. So this is a setup. This is A and B. Now I will calculate the difference using the given relation, that is HA minus HB is equal to H3S3 minus H1S1 minus H2S2. So let me directly put the given relation. I will put it as HA plus H1S1 plus H2S2 is equal to HB plus H3S3, which means the relation was derived from this formula only, HA minus HB, this relation. So this becomes HA minus HB, this is equal to H3S3 minus H1S1 minus H2S2. Putting the values, H3 is equal to H2, which is 0.342, H1 is 2.5. So H3 is 0.342 into specific gravity of the given oil 0.8. H1S1 is for the carbon tetrachloride, which is 2.5 meters into its specific gravity 1.594 minus, that is for mercury, 0.342 is the pressure head difference into specific gravity of mercury, that is 13.6. So we got this value as minus 8.3626. This is the value, and I have to put it here, meters of water. So this is what they have asked, difference in the mercury level, calculate the pressure difference between A and B, that we have gotten. Now also we can calculate this pressure difference in the actual pressure terms, that is kilonewtons per meter square. That also could be calculated like we calculated in the previous numerical. Here you could see we had put the value P is equal to W into H, right. Here what is pressure difference? That is delta P, we will see delta P, change in pressure. This is equal to PA minus PB. What is this? This is equal to rho G delta H. So this is equal to rho, that is density of water, is 1000, G is 9.81, and delta H is the change or the difference in the pressure. So this is also delta H, this value. So multiplying this by delta H, there is a negative sign here, minus 8.3626. This value turns out to be minus 82037 newtons per meter square approximately. So if I need to put it in the kilonewtons per meter square, I will just divide it by 1000. This is 82.037 kilonewton per meter square. So this was majorly regarding the manometer. We discussed about the manometer with one end connected to the pipe. Then we discussed about the differential manometer when both the ends are connected to the pipes, and their difference pressure head is also being calculated in the terms of meters of water, in the terms of the kilonewton per meter square. So this pressure difference H value could be put here. I could put H is equal to minus 8.3626 meters of water, or it is actually delta H, and delta P is equal to minus 82.0371 kilonewtons per meter square. Next is hydrostatic forces. When we talk about the properties of fluid, when we talk about fluid mechanics, hydrostatic forces based upon the hydro is very important. What is hydrostatic force? It is a force that is a resultant force exerted by fluid at rest on a submerged surface due to the pressure created by the weight of fluid above. That is the hydrostatic force, because of the weight of the whole fluid. So depending upon the weight of the fluid, that is the overall volume of the fluid is proportional to the weight. This height is the major thing, that is to what level the fluid height is there, that is putting pressure over it. So that is proportional to the height here. It acts perpendicular, that is normal to the surface, and increases with depth because fluid pressure increases with the height of fluid column above the surface. So it is very important to understand hydrostatic forces. What is total hydrostatic force? That is a function of rho G A H. That relations also I have put here. F is equal to rho G A into H bar, where you can see rho is density of water. When I am talking about hydrostatic forces and I am talking of water, rho is density of water proportional to density of the water or density of the fluid, which is of interest. Then G, because we are talking about hydrostatic forces acting upon or against gravity, G will also come into play, right. Then A is area upon which this fluid is acted. H bar is depth of center of gravity of the plate below the free surface. Here H star, that is point of center of pressure, it is known as H star, or some notations will call it as HCP. CP means center of pressure. That is equal to Ig by AH bar plus H bar. That means Ig is second movement of area, that is movement of inertia of the plate about the horizontal axis through centroid. Now this moment of inertia divided by the area into h bar plus h bar, that is depth of the center of gravity of the plate below this free surface, that is what is h star, which is to be calculated in general, that is depth of center of pressure. I will just draw one simple diagram, from there you will understand that better. And before that, let me read the statement. Here itself I will draw that diagram. It says, determine the total pressure on a circular plate of diameter 1.5 meter which is placed vertically in water in such a way that center of plate is 3 meter below the free surface of water. Find the position of center of pressure, that is h star is to be found. It says a circular plate is placed below water, that is, for instance, here we have water down here and we have a circular plate here. Center of plate is 3 meter below the free surface of water. Let me call this point as center of plate. It says this is 3 meter from the surface of water. If I say this all is water, right, and here we have this plate kept here in water. Now they say this center of plate to the surface of water, this height they say is 3 meter. What is this height? This is h bar, that is mentioned here. H bar is depth of center of pressure below the surface in meter. Now here we need to find the h star, position of the center of pressure. In this plate, the center of pressure might not be exactly what is the center of the plate. Center of the pressure could be another point. Let me locate a point here. Suppose this is my point G. I call this at point G. There is another point, let me say P here, point P, that is a center of pressure, and this distance or this difference from the surface to the center of pressure is h star, and this is point P here. Now to find total pressure, we will use the relation F is equal to rho G A h bar, and what we are given is h bar is equal to 3 meter, diameter of plate, that is I will put it as D, that is 1.5 meter. Now to calculate F, I will put the value of rho, that is density of water, as 1000 kilogram per meter cube, and anyway G is always 9.81 meters per second square. Now I will put these values here. F is equal to rho G A into h bar. For this I need to calculate first A. What is A? Area is equal to pi by 4 d square, which is equal to pi by 4, value of d is 1.5 meter, this square. This value of A turns out to be 1.767 meter square. Putting all these values here, rho G A into h bar, rho is 1000, G is 9.81, A is 1.767 and h bar is 3 meters. Therefore, I got the value of F, that is the total pressure, as 52 kilonewton. This is total pressure. Now they say find position of the center of the pressure. Total pressure part is over. This is part 1. Part 2 is find the center of pressure. That is part 2, that is position of center of pressure, which is H star. This is equal to moment of inertia, that is second moment of inertia of the plate about horizontal axis, that is through the centroid, by A into H bar plus the H bar, that is distance from center of the plate. Here first we need to find Ig. What is Ig? The second moment of inertia, that is pi by 64 d power 4. When I put the values here, this is equal to pi by 64 into 1.5 power 4. This is equal to 0.2485 meter to the 4th degree. Putting all these values here, again I am putting the relation H star is equal to Ig by AH bar plus H bar. This is equal to value of Ig 0.2485 by area into height 1.767 into 3, that is height of the center of gravity of the plate below the free surface, that is H bar, plus this height, that is 3. This gives me the value of H star, that is the center of pressure, the position of the center of pressure, as 3.0468 meters. That means here H star value is 3.0468 meters. That is the position of the center of pressure. So this was only one numerical I took for the hydrostatic forces. Now I will come to the properties of fluid. Properties of fluid, lot of properties are discussed in the lecture series. I will only take some numericals on some of the properties. For instance, I will just recall the properties and I will take some examples on capillarity, maybe on specific gravity, that part I will take care. To recall, what is density? That is rho. Density is anyway mass per unit volume, that is mass of the fluid per unit volume. Its units are kilograms per meter cube. Then we have specific weight, which is W or gamma. Definition: the weight of the fluid per unit volume. It shows how heavy the fluid is in a given space. That is W is equal to rho into G, which is given in newtons per meter cube. Then comes specific gravity, Sg. Definition: the ratio of density of the fluid to the density of water, that is for liquids, or density of air for gases. When we are talking about fluids, both liquids or gases could come into play. So this is density of fluid per unit density of water. This is what is specific gravity. Weight of the fluid is force exerted by gravity on a given mass of fluid, that is mass into G, that is in Newton. Let me see a very simple problem statement here. They say calculate density, specific weight and the weight of 1 liter of petrol with specific gravity 0.7. So what we are given is volume. Volume is 1 liter, that is 1000 centimeter cube. To convert this into meters, I can divide this by 10 power 6. So this becomes 1 by 1000 meter cube. Specific gravity, they say Sg is given as 0.7. That is, we have been given this value Sg, that is rho of the fluid, or here in this case petrol, per unit rho of water. We are given this. This means rho of petrol, that is density of petrol, is equal to 0.7 into density of water. To put the value of density of water, this is 0.7 into 1000. The density turns out to be 700 kilograms per meter cube. This is first part. Second part they asked about is specific weight. For specific weight, I can put this relation. Specific weight is W or gamma, which is rho into G, right? This specific weight is rho into, how did we come to rho into G? That also I can derive here. For example, W is weight of fluid per unit volume of fluid. This is equal to W per unit V. What is this W? W is M into G. That also you can see it here. W is M into G here. And mg by V gives me m by V into G. M by V is what? Rho. Rho G. So I'll put the values of rho and G. Rho is 700, that is for fluid we are talking about, that is petrol, into G is 9.81. This is equal to 6867 newtons per meter cube. Now the third part, they are asking about weight of the fluid. Weight of the fluid I can put this relation also here. Weight of the fluid is m into G, that is mass into G, or I can use this relation directly here. Specific weight is equal to weight of the fluid per unit volume, that is weight of the fluid is equal to specific weight into volume, which is already calculated. Specific weight is 6867, and volume we have seen here is 1 liter, that is 1 by 1000 meter cube. I will put this as 1 by 1000. This turns out to be 6.867 Newton. So these were very simple calculations. Now I will try to talk about surface tension. Surface tension is very important when the fluid is stored anywhere. We try to talk about the hydrostatic forces below the surface, depending upon the weight of the fluid, depending upon the height of the fluid, from the base or from the center of the body or from the center of pressure of the body, what is the force or what is the load that is hydrostatic. At the surface there is surface tension. Surface tension concept could be recalled here. Surface tension is the property of liquid's surface that makes it behave like a stretched elastic film or membrane. This happens because molecules at the surface are pulled inward by cohesive forces from the liquid below, minimizing the total surface area. You can see there is a clip kept here because of the surface tension. If you make the clip to completely dip into the liquid or this water, it will go and sink there. Because surface tension, it does not sink. Surface tension causes the surface of liquid to resist external forces, allowing objects heavier than liquid like a small insect or a razor blade to float without sinking. It is just because of surface tension only lot of the objects float on the liquid bodies. It is measured as the force exerted along a line of unit length on the liquid surface, and SI units is force per unit length, that is Newton per meter. To put the relations here, surface tension F is equal to T times 2 into L plus T, where T is surface tension here. It is given here. F is force due to surface tension, and L and T are the length and thickness of the plate on which the surface tension is exerted upon. These are all given in meters here. Apparent weight of the plate. So apparent weight is W apparent, which is W plus F. Actual weight plus forces due to surface tension. This is the apparent weight. Let me see a problem statement here. A square glass plate of length 10 cm and thickness 0.4 cm weighs 40 grams in air. It is held vertically such that its lower edges rest on water surface. What is the apparent weight of glass plate now? Surface tension of water is 0.073 newtons per meter. it says the glass plate has this dimension, 10 centimeter length, 0.4 centimeter thickness. Let me put these values. L is equal to 10 centimeters, which is equal to 0.1 meter, and thickness is equal to 0.4 centimeter, which is equal to 0.004 meters, which is 4 millimeters. Weight of the plate W is equal to mg. What they are telling is there is a liquid contained in a container in this container. We have a plate kept here of thickness 0.4 and length 10 centimeters. This is a, they say, glass plate. So this is glass plate where they have given the length as 10 centimeter and thickness here as thickness is 0.4 centimeters. Now weight is equal to m into g. This is weight of plate. Because we have been given the value of m, that it weighs 40 grams in air, it is 40 grams into g, that is 9.81. This weight turns out to be, if I need to calculate this in newtons, this 40 is, I will say m is equal to 40 gram, which is equal to 0.04 kg, because I am need to talk about SI units. So this 40 grams into 9.81, or I will better put it as 0.04 into 9.81. This is in newtons. This is 0.3924 newtons of weight. Now they are asking about apparent weight. For the apparent weight, we have seen apparent weight is the weight in air plus the weight or forces due to surface tension. So apparent weight is regular weight in air plus weight due to the surface tension, that is, it is higher than the regular weight. Now forces due to surface tension. F is equal to T into 2 times L plus T. Putting the values, we can say F is equal to T, the value is given here, surface tension of water is, that is T is 0.073 Newton per meter. That is here T is equal to 0.073 Newton per meter. This T is at the surface. This is 0.073 times 2 into length plus thickness. Length is 0.4 meter and thickness is 0.04 meters. This gives me the value of F as 0.015 Newton. Now apparent weight, that is weight due to surface tension, is weight in air plus force, that is due to surface tension. This is equal to, W is calculated here, 0.3924, 0.3924 plus F is 0.015. This turns out to be 0.4074 newtons. So this is surface tension. I am taking one numerical each. In each concept, for example, surface tension, I have taken one numerical. You can take simple or similar numericals to practice your own, and then you can come to the forum, that is, they can ask questions if you have any problem or face any challenge there. We will try our best to come to solve your problems here. Now, next concept is capillarity. Capillarity is the natural ability of a liquid to flow in a narrow spaces or thin tubes without external forces, often against gravity. This is due to combination of surface tension and adhesive forces between the liquid and the surface of the tube. Whether we talk about water being absorbed by plants or ink coming to the tip of the pen or water being absorbed by towel, this is all due to capillarity. So, capillarity as a property is the ability of a liquid to flow into narrow spaces or thin tubes. It occurs because of adhesive forces between the liquid molecules and the solid surface can be stronger than cohesive forces within the liquid, causing the liquid to rise or fall inside the narrow space. For instance, here the forces are lesser, here the force becomes high, so it rises here. This is capillary attraction, right? Also, there could be capillary repulsion because mercury is having higher specific gravity. There is a capillarity repulsion here as well. Capillarity is responsible for phenomena such as water rising in thin tubes, absorption of water by paper towels, movement of water in plants from roots to leaves, and functioning of wicks in lamps. So, this is known as meniscus, this curve here. This is lower meniscus, and this in case of mercury, upper meniscus, this is there in capillarity. Now, when we talk about some relations or some formulas in capillarity, the capillarity effect in a tube is given by H is equal to 4 sigma cos theta by rho g d. Here H is again height, that is rise of the liquid due to capillary action, that is capillary rise, that is H is there. Here sigma is surface tension of the liquid, theta is angle of contact between the tube wall, that is in degrees, rho is density of liquid in kilograms per cubic meter, and the sigma is same as what was given as T in the previous relation. This is surface tension T. So, do not confuse with this T here. So, we need to understand that I just have put or given another notation here, that is sigma, that is surface tension. It is sometimes given as sigma, sometimes given as T. In this relation, I put it as sigma because in the numerical that I will discuss, I will also have T, where T would be temperature of the liquid. That is why I put the notation sigma here, that is surface tension of liquid. Angle is angle of contact between liquid and tube wall, that is in degrees. Rho is density. Now, let me see this problem statement. Calculate the capillary effect in millimeters in a glass tube of 4 millimeter diameter when immersed in water and when immersed in mercury. So, I will draw it here. First, I will draw for maybe water. To recall, for water, it will be rising high. For mercury, it will be coming low, and the meniscus would also be different. That is, for water, if I draw and there is a tube immersed here, I would have to draw it in this way. This is water here, and for the water, there would be rise in the level here. It says the temperature of the liquid is 20 degrees centigrades. Temperature T is 20 degrees centigrades. The value of surface tension of water and mercury at 20 degrees centigrade in contact with air are 0.73575 Newton per meter. This is for water, that is sigma for water is 0.07. It should be 0.073575 Newton per meter. This is sigma for water, and we have sigma for mercury. I will put sigma for Hg, that is given as 0.51 Newton per meter. The angle of contact of water is 0. Here the angle of contact for water is 0 and for mercury is 130. That is theta for water is 0 degrees and theta for mercury it is given as 130 degrees. Take density of water as 20 degrees equal to 998 kilograms per meter cube. Rho they say is 998 kg per meter cube. So here we will have a meniscus like this. That is, water will have a lower meniscus. We put it as lower meniscus. Now let me calculate what they have asked, that is capillary effect in millimeter in a glass tube, and the diameter of glass tube is 4 millimeter. Diameter is also given as 4 millimeter, that is D is 0.004 meters. Let me try to put the values there. For water, that is part A. For water, I will put H for water is equal to 4 sigma for water into cos theta by rho for water into G into diameter of the tube. Here diameter of the tube they say is 4 millimeter. This is 4 millimeter only, and there is an angle theta here of this meniscus. This angle theta is 0 degrees in water. It is no angle is there even. So let me put the value. This is equal to 4 into surface tension of water. The surface tension of water is 0.07. It should be 0.073575. 0.073575 into cos theta, that is cos 0 degree. Cos 0 is 1 into rho of water, that is given as 998 kilograms per meter cube at 20 degrees into G, that is 9.81 into the diameter in meters of the capillary tube 0.004. This I got the value as 7.5 into 10 raised to power minus 3 meter, or I can put that in millimeter as well. This is equal to 7.5 millimeters. So this is the capillary rise in water for the given specifications, given values, the parameters. Now for mercury. For mercury, that is Hg, the figure would be something like this. They say the angle is also there and there would be capillary downfall here. For instance, if I have a mercury here and a tube of 4 millimeter immersed here, it would be something like this. There is mercury field here. I have taken a darker color here. So when a capillary action happens in mercury, it falls down here and there is a upper meniscus here. So here it is something like this. So here they have also given there is an angle of 130 degree. That is, this theta is 130 degrees. This is upper meniscus. Though in the water we have lower meniscus, but here there is no meniscus because angle is 0. This means no meniscus is there. This is again 4 mm thickness of the tube. Now putting again those values here, we have the rho for water given here as 998. I will also put rho for mercury is in kilograms per meter cube, it is 13600 kilograms per meter cube. And the same relation could be put here. H for mercury, this is equal to 4 times the surface tension for mercury, and cos of the angle, that is for the mercury, that is given rho for mercury into G into the dia of the capillary tube. Putting all these values, this is similar to the previous relation. You can just calculate it, I am leaving it for you. You will put all the values and try to find the value. You will find this in negative form. You will find this value as 2.408 into 10 raised to power minus 3 meters, and this is negative value because it is lowering down. This can also be put as minus 2.408 millimeters. This you can calculate by yourself. With this, I am closing the introduction to fluid mechanics tutorial. I will talk about fluid mechanics, and more properties and other parts of the fluid mechanics will be covered in the next tutorials. Thank you.